Yes, so welcome everybody. It's a great pleasure for me to introduce today's speaker, which is Serge Haroche from École Normale Supérieure and the Collège de France from Paris. Professor Haroche got his PhD in '71, working with Claude Contanucci, whom some of you may know later got the Nobel Prize. Then he also had a year as a postdoc, working with Shallow, who also won the Nobel Prize. And then in 1975, he came back to Paris as a full professor. Now, in Paris, Serge Haroche has been on a very, very long journey. More than 30 years ago, he started up a project that he will essentially tell us about today. The quest he started was he wanted to control really the smallest constituents of matter, light in the terms of single photons and single atom. Now, this has been a very, very tough experiment to do, but also a highly successful experiment, which he has really pushed from nothing to being a beautiful and fantastic experiment that we can do today. So the motivation for much of these works comes from quantum mechanics. Once we get to these very small level of things being as small as a single atom, then much of the understanding of how nature works that we have in our minds just breaks down. At those scales, you need the theory of quantum mechanics. Now, when I'm not here speaking to you, I also have the pleasure of teaching the Quantum Mechanics 1 course to our undergraduates. And when they learn about quantum mechanics, they always sit like that, pulling their hair out, because quantum mechanics is just so weird. And it's not just because I'm a bad teacher, it's also because quantum mechanics is just fundamentally very, very difficult. Even to the founders of quantum mechanics was very, very difficult. There are very famous debates between Bohr and Einstein where they were discussing back and forth about how is all of this quantum mechanics, can it really be true? And in particular, Einstein refused to believe that the world was like this. No, the world cannot be this complicated. God does not play dice, Einstein said, to which Bohr replied, stop telling God what to do. Okay, so these arguments here are not your standard physics argument. Now, normally in physics, God doesn't play a big role. But the problem that they had back then was that making experiments with single atom and single photons was just impossible. Even another one of the founding fathers, Erwin Schrödinger, who was really one of the founders of quantum mechanics, said that, no, you're crazy to think about experiments with single photons, single atom. It will never happen. Well, that was just wrong, because as I said, 30 years ago, people like Serge Haroche sets out to say, okay, we really want to control these constituents of light and matter at the most fundamental level, such that these debates that used to take place between Bohr and Einstein, what is nature, what happens when at this very small scale? Well, today this is something that you can just go into the lab and observe and see what really happens. So where it used to be a philosophical discussion, now it is really a physics question, because you can go in and actually do the experiments. So what these experiments have shown is that nature is just a fundamentally weird place. There are things going on which is almost beyond our belief. So what the experiment that Serge Haroche has been doing has really teaches us a lot about what goes on at this level. Now we can really go into the lab, and all the things that Bohr and Einstein could only dream about observing, now we can actually observe them, and we can see that indeed nature behaves much different than what we expected. And this has been a very, very educational and has taught us a lot about physics and about how nature works. I remember in particular when I was a young student, I was reading through the papers of Serge Haroche and trying to grasp what was going on, and by really working through these papers, I really learned a lot about quantum mechanics. And due to this long and dedicated effort, taking more than 30 years, indeed, we are by now much smarter than we used to be. So, and not only me, but all of physics community, and therefore in 2012, Serge Haroche, together with Dave Wineland, was awarded the Nobel Prize in physics for the work that we will see up here in just a second. So please welcome Serge Haroche.
So, thank you very much for this very kind introduction. I think you said almost everything. So I am very pleased to have this opportunity to talk today about the research that I've been carrying out for a very long time in Paris. And I like to illustrate this experiment with this picture, which shows two hands juggling with red balls bouncing between mirrors. In fact, the balls I am considering here are not material balls. They are grain of light, photons. And it's very challenging to do this kind of experiment with photons because, as you know, an important part of juggling is to look at the objects you are juggling with. And when you look at photons, usually you destroy the photons. Light is destroyed upon detection. And what we want to do in this experiment, instead of destroying the photons, is now we are destroying the photons. Okay, so we want, in fact, to find a gentle way to measure photons without destroying them in order to be able to prepare light fields in these strange counterintuitive quantum states that Dr. Sorensen alluded to in his introduction. And I would like to describe this experiment, but at the same time, I also would like to give you a kind of historical account, just to illustrate how basic physics is working. In fact, it's very important first to be in the right environment, to have the right teachers and mentors, and to be able to work in an environment which is conducive to free research. It's also very important to realize that you don't give yourself a goal from the beginning. We did not start 40 years ago by saying we want to detect single photon and single atoms. It just started doing things very often in a serendipitous way. We got triggered to try to do other things, and eventually we build up something which in retrospect seems coherent and continuous, but in fact which is based on lucky events, on change of directions due to observations. And this is the way basic research is working. Of course, you need some kind of luck to do that, and my first luck was to start my research career when the laser was invented. It was a long time ago, but it was very exciting to be in a physics lab at that time. You see here a picture of the first Ruby laser back in 1961, and I started doing my PhD in '65 at a time when the lasers were being developed, and it was quite clear that the way to be able to tame light, to have light with very precise direction, coherence, monochromaticity would become very important, not only for applications that we see in our everyday life now, like CD or DVD players or optical fiber communication, but also in basic research. We understood from that time that lasers would be fantastic tools to manipulate and to learn things about atoms. We did not know exactly what we could do, but it was a very exciting time to think about all the possibilities. I was also very lucky to start my PhD in a lab where the fruitful ideas were developed every day to manipulate matter with light. These were the ideas of optical pumping. And I like to show this picture, which was taken in October 1966 when Alfred Kastler was the head of the lab at that time, got his Nobel Prize in physics. In fact, Kastler and Brossel, who were working together, invented back in the 1950s optical pumping. The optical pumping is a method which I will say a few more words about, which consists in exchanging angular momentum between light and matter, being able to prepare matter in a state which is out of equilibrium, with which a lot of interesting things can be made. On the left of the picture, you also see a young man Claude Cohen-Tanucci, who was a student of Castellan Brossel, and who became my own thesis advisor. And Claude Cohen-Tanucci, for his thesis work, discovered light shifts, the fact that light is able to modify the energy levels of atoms, and the light shifts were going to play a very important role at later times in atomic cooling and trapping experiments. And as has been recalled, Claude got a Nobel Prize in Physics for that in 1997. And between Castellan and Brossel, you can see me. I was a young graduate student at that time. I was smiling because it was really dazzling for me to have come quite by chance in a lab where such wonderful things were being developed. And I was very far from thinking at that time that one day I would also be recognized for physics which stemmed directly or indirectly from the work that Castellan, Brossel, and Cohen-Tanucci had developed. So I have to say a few words about optical pumping first. Optical pumping consists in manipulating atoms and the internal state of atoms with light. In fact, there is a variety of atoms called paramagnetic atoms which carry a small magnet, a small angular momentum, which is a small magnet proportional to what is known as the spin of these atoms. In ordinary matter, in a gas, the spins or the magnets of different atoms are randomly distributed. But what Castellan and Brossel discovered is that if you shine properly polarized light on an ensemble of such atoms, you can exchange momentum between the photons and the atoms and orient all the spins along a given direction. So you get an oriented sample, and the light that this sample is absorbing or emitting depends upon the degree of orientation. So you can use at the same time the light as a way to prepare the sample, and by detecting the photons as a way to observe the degree of orientation and how this orientation changes when you do things on the system. And the first assignment I was given at that time by Claude Cohen-Tanucci was to perform magnetic resonance on this system. That is, you add the radio frequency field, and you try to find the frequency which would flip the spins and thus change the way the light is transmitted by the system. And you see here the result of this experiment. This is the first experiment I ever did. I recorded the spectrum of this magnetic moment as you tune the frequency of the magnetic field, which is the same, and we see resonances corresponding to the flipping of the spin when 1, 3, 5 photons were absorbed. So I don't want to enter into the details of this experiment, just to tell you that I was very proud because it was the first time I did something in the lab, and also because this experiment involves atoms interacting with photons, which would be the subject of my interest from that time on. But in this experiment, the atoms were very, very numerous. You had billions of atoms in the sample, and they were interacting with zillions of photons. And when you have huge number of atoms and photons, you can understand everything almost classically. It is only when you decrease the number of particles down to a few that the quantum effects become conspicuous. And so what we are doing now is the same kind of experiment but with a single atom and a single photon. But it has been a very, very long adventure to get to this point, and I would like to talk to you a little bit about it. The other thing I would like to mention are light shifts, because they also play an important role in my work. As I said, Claude Cohen-Tanucci discovered that the atomic energy levels are shifted in a non-resonant light field. Non-resonant means that the atoms cannot absorb or emit radiation because it does not match energy conservation, but still there is an effect, and the energy levels of the atom are slightly shifted by the light, this shift being proportional to the light intensity. This effect was discovered as a curiosity at that time, and nobody knew what it could be used for. But it has been very useful for cooling atoms with light. You see here a geometry of two counter-propagating light beams. If they propagate one against the other, they form a standing wave. They form a structure in which the electromagnetic field is going up and down spatially. And you see here what happens to an atom when it propagates in this standing wave. You see, as the standing wave is going from low intensity to high intensity, the energy of the atom is shifted, and you get a periodic variation of the atomic energy. It means that when the atom is going from this point to this point, it has to climb a hill, it loses energy, and it's slowed down. Now, another important effect here is that the position of the field maxima and minima depends upon the spin of the atom. For spin up, you have this potential curve. For spin down, you have that potential curve. And what Cohen-Tanucci discovered later on is that you can combine this energy shift effect with optical pumping so that you can force the atom when they are at the top of a hill here to fall down here and to have to climb the hill again. And this perpetual climbing of the hill was cooling down the atom. It was always losing energy up to the point when the atom was put to a standstill. This effect was called Sisyphus effect in remembrance of this hero of the Greek mythology, which was forced by gods when it was at the top of the hill to go back down and to raise the hill again. But here it's not God which is doing that, it's optical pumping. And the combination of optical pumping and light shifts gave rise to the most efficient way to cool atom down. When the atoms are very cold, you can organize a laser field to make a standing wave in two directions, or standing wave in a plane to have a lattice of potential wells, or in 3 dimensions to have a 3-dimensional lattice. And these very cold atoms can be kept by the light shifts, that is, by this position-dependent energy shift at the bottom of the wells, as you keep eggs in a box. And this is called an optical lattice, and it's a very useful and convenient way to prepare atoms in ordered structures, and a lot of experiments are now being performed with that. So I just wanted to recall this to tell you that results which were obtained 50 years ago by Claude Cohen-Tanucci and which seem to be completely useless have become really the main ingredients for a lot of experiments which may lead to applications today. But here I am going away from the main topic of this talk. When I left Paris after my PhD, and I knew a lot about optical pumping and about light shift, I went to Stanford, as has been recalled, and I was lucky to work there with Art Shallow and Ted Hench, who was a young assistant professor of art at that time. You see here a picture showing them in their lab, and it was much before they each got a Nobel Prize for different reasons in 2005 and 1981. And at that time, they were playing with the newly developed dye lasers, tunable lasers. Lasers, you just turn a knob and you can change the frequency of the laser continuously, which were a fantastic tool for spectroscopy. And I learned there to use this laser for spectroscopy. I learned to use dye lasers, and I started to ask myself, what can I do with this dye laser, something new and original? So when I came back to Paris in 1973, I had to ask myself the question that any young scientist has to ask him or herself when they come back from a postdoc. What can I do to put in use what I have learned to do, but to do something new and original? You see, I am here pictured with my first 2 graduate students, Michel Gross and Claude Fab, turning the back to the camera, and we were trying to find out which would be an interesting field to enter in. And we decided it would be very interesting to use laser light to excite atoms into Rydberg states. Rydberg states are states in which one electron is promoted to an orbit which is very large in size compared to ordinary atoms. And these atoms were supposed to have very interesting properties. By back-of-the-envelope calculation, one could find out that they were very, very interesting as probe of very small perturbations. But of course, they were very difficult to prepare and to observe in the lab. Before the lasers, it was impossible. You did not have the intensity and the monochromaticity for the laser required to excite selectively one Rydberg state. At that time, I had to write a review article for a popular magazine, and I drew this kind of semi-artistic picture of a Rydberg state. This represents a section of a Rydberg atom through a plane passing by the nucleus, and it's an atom which has an S, it's an S state, it's a state which has a spherical symmetry around the nucleus. And these dashed green areas correspond to the maximum probability density for the electron. So they make, as you see, concentric circles around the nucleus. And the important point is the size. You see here 100 angstrom. These atoms are thousands of angstrom in size. And compared to a ground state atom here, which is just a very small point, or even to a DNA molecule, which is made of thousands of atoms, they are really huge. They are the size of biological objects. So we were fascinated by the fact that if we could prepare and manipulate these atoms, we could do things that no one could have done before. And so we embarked into these studies. To prepare these atoms, we just have to look at the energy ladder of the atomic states. You see here for sodium atom, the ground state is labeled 3s by spectroscopists, and the first excited state is a 3p state. In order to excite this state, what you have to do is to use a laser which is resonant with this transition. And then before the atom has time to go down, you excite with a second laser, so it's a stepwise excitation as you climb a ladder, in fact. And with another laser, you can excite states which have much more energy and which lie very close to the ionization limit of the atom. And so you see here that you have a kind of, at that time it was a terra incognita of levels that nobody had studied in the lab, but which you could now excite with a laser field. And as you get close to the ionization limit for a given energy, you have a lot of levels which differ from each other by their angular momentum. And spectroscopists have called them SPDF for increasing value of the angular momentum until you get to the highest possible angular momentum, which is a circular state atom. It's an atom in which the electron goes around the nucleus on a circle. In fact, I have replaced this circle by a kind of running wave using the pictures that De Broglie made of matter at the quantum level. The electron behaves as a wave, and this wave is going around the nucleus. And what we call the principal quantum number of the atom in this picture is the number of waves that you have around the circle. So you see all these states became now available for research, and you see that the transitions occurring between these states fall in the millimeter wave range. So we really wanted to explore this millimeter wave spectra, and for that we shined light on Rydberg atoms and look at the transition between the states. In fact, it was not the first time microwave transitions were studied in this context. 10 years before, in the 1960s, astronomers have observed microwave radiation coming from outer space, which corresponded to the transition made by Rydberg atoms prepared in the interstellar medium by collisions of electrons and ions. And we really wanted to observe this phenomena in the laboratory. I want also to emphasize the fact that this circular atom, which was going to play an important role in our experiments, is in fact the atom that Bohr described in his early model of the atom in 1913. What Bohr said is that the electron is going around the nucleus on a circle, and you have to quantize the orbits, and the quantization condition which Bohr introduced was to say that the electron must have an integer number of Planck's constant value in its angular momentum. And this is equivalent to saying that you must have an integer number value of De Broglie wavelengths around the circle. So you see that Rydberg atom, at the time we started studying them, had already played an important role in physics. Rydberg had found the formula for the position of the levels. Bohr had interpreted it in terms of his old theory of quanta. Astronomers had observed it in outer space, and the development of laser made it possible to prepare and observe them in the lab. On this picture, I just give you another view of this Rydberg atom. You start with a very small atom, about 1 angstrom in size, and by laser excitation, you promote an electron on a very large orbit. And you see that the ionic core, which is made of the nucleus and the other electrons, is very small at the scale of the large orbit. And so this electron sees basically a point charge, and so Rydberg atoms behave as hydrogen. The position of the energy levels is given as in hydrogen by the famous Rydberg formula. R is a constant introduced by Rydberg, and n is the principal quantum number. And when you climb the ladder of states, you go from n equal 10 to 20, 50, 100, and you go to larger and larger Rydberg states. Delta here is called a quantum defect. I won't talk about it here, but it's just a small change to the principal quantum number due to the perturbing effect of the core, to the fact that the core is not just a point charge. And what is very important is that this system, which looks like hydrogen, has a very big size. The size of the atom scales as n squared, and it has a long lifetime, and it is extremely sensitive to external fields, to microwave radiation, and to interaction with other atoms. And Rydberg atoms have since then been a topic of constant interest in atomic physics, not only for the experiment I'm describing, but for experiments extending up to now, and especially the interaction between Rydberg atoms is now a very important topic in atomic physics and in quantum optics. How do you detect these Rydberg atoms? For that, you use electric fields. You use the fact that they are very sensitive to perturbations. You see here the Coulomb potential, the 1/r potential, which keeps the electron close to the nucleus. And you have here these two horizontal lines represent the energy levels of two neighboring Rydberg states, which I'll call E and G. If you want to detect the Rydberg atom, you apply an electric field. This electric field derives from a linear potential varying linearly in space. And you see that adding the electric field to the Coulomb potential lowers the energy barrier at one end. And the upper state, which occurs at the top of this barrier, is able, the electron in the upper state becomes able to escape. And so you ionize the atom, you lose the electron, and you get on your electron detector a click which tells you that the atom was in the upper state. The lower state is still protected. If you want to ionize the lower state, you have to raise the electric field in order to increase the slope. And one convenient way to do that is to apply a ramp of electric field, which reaches at different times the ionization threshold for the upper and lower level. And so you will get time-resolved electron peaks, which will tell you whether the atom was in one state or in the other. This method is the one we are using up to this day. And you see that if you are only two levels involved in the experiment, you get 1 bit of information per atom detected. In fact, this method was developed at the same time that we started doing this by Dan Kleppner and his students at MIT, and Kleppner has become a close friend and a close competitor too for all this physics, and this is the way also research is going on. We have friends and colleagues and competitors all over the world, and a lot of emulation which helps this going. So what can we do with the giant Rydberg atoms? Can we use their huge sensitivity to radiation in order to get to the point where you will see the interaction of a single atom with a single photon? This is the question that we started asking ourselves at the beginning of the 1980s. Second question, can we use Rydberg atom in order to detect photons without destroying them, which is a little bit more tricky because usually by photoelectric effect, you have to absorb the energy of the photon to detect it. And last question, if you are able to observe the photons without destroying them, can we use Rydberg atoms to manipulate these photons in order to prepare quantum fields with strange properties, Schrödinger cat states, for instance? Of course, we did not ask this question one morning just coming to the lab. These questions came up from long discussions after we had performed many experiments. And what we found when looking at that is that it was very useful to have the Rydberg atoms interact with photons in a cavity, in a good cavity, to protect the system from the environment. The cavity being a kind of stage in which this photon-atom interaction would occur under the cleanest conditions. So this physics interacting atoms with photons in cavities has been named cavity QED, cavity quantum electrodynamics, and this is a field in which we started working about 30 years ago. In fact, when we discussed these early ideas, I was still a young professor in my lab, and I just show this picture because you can see here on the right, Jean-Michel Raymond was at that time a student of mine, and he has stayed with me over all these years, and we have been sharing ideas and interacting with each other, and nothing would have been possible without our collaboration. You see here also a discussion with Daniel Kleppner at Les Ouches Summer School in 1982, where we were discussing whether it's possible to get to the point where a single atom interacts with a single photon. And in fact, our experiments were triggered by, our ideas were triggered by the experiments we were performing then back at the end of the 1970s. You see the setup we are using was quite simple in its principle. We have an atomic beam. We cross this atomic beam with lasers which excite Rydberg atoms here at the intersection. And then we send microwave to induce microwave transitions. And at the beginning, it was just in order to define precisely the interaction zone, we had a cavity, an open cavity made of copper mirrors, just to define the mode of the field. Once the atom had interacted, they drifted downstream, and here an electric field was applied in order to detect the transition between the states. And you see the kind of signal we obtained. You have this peak correspond to the upper state of the transition, 27S, this peak to the lower state of the transition, 26P. And you see that when the cavity is off resonance, you have mainly the initial state, and when the cavity gets on resonance, you have a huge increase in the transition to the lower state. And you did not have to apply any microwave to do that. In fact, we could switch off the microwave by merely getting the cavity at the right frequency. We force the atom to emit photons on this transition. Of course, this effect is well known. It's a Maser effect or a laser effect. When you invert the population in an atomic system and you have a cavity sustaining the transition frequency, you get a large emission. But the striking point here was a very low threshold. In an usual laser or Maser, you need billions of atoms to get the system lasing or masing. Here, we needed only 200 atoms. And so, in the conclusion of the paper, we said that we wanted to extend this to very small absolute atom numbers. So this was the beginning of this hunt towards cavity QED. Is it possible, by increasing the quality of the mirrors, to get to the point where the threshold would be only one atom? So the first idea then was to change the copper mirrors into superconducting niobium mirrors, which have a much higher reflectivity. So we did that, and a couple of years later, we were able to observe the effect in a high Q superconducting cavity. We were able to observe what we call cavity-enhanced single-atom spontaneous emission. We have an excited atom, and the atom is forced to emit in the cavity just because the cavity has the right frequency. So this is the limit of a Maser when the amplifying medium is made of only one atom. And this, you see here the kind of signals. Each atom gives a click, and you see that the position of the click changes when the cavity is put on resonance. You get clicks at an earlier time when the cavity is off resonant, then at a later time when it is on resonant. And when you average over many realizations, you see that you get an effect down to something of the order of one atom at a time in the cavity. So we were very happy about that, but we are not still satisfied. In fact, what we wanted to get was a regime in which the cavity would be so good that the photon could stay in the cavity long enough to be reabsorbed by the atom before it decays in the mirrors. This is what is called the vacuum Rabi oscillation, and I have tried to show it here. You have these two-level atoms. The atom is initially in the excited state, and the cavity is empty. So the system enters in the cavity with the atom excited and zero photon inside. Then the atom goes from E to G, and one photon appears in the cavity. But if this photon can stay long enough, at a later time, the photon will be absorbed, and the atom will go back in the excited state. And in fact, we have here a situation which is encountered in quantum physics very often. It's called a two-level system. The system oscillates between the state E0, excited atom and zero photon, and the state G1, atom in the lower state and one photon. This is, of course, if the cavity is at resonance with the transition. So we wanted to observe what we call the vacuum Rabi oscillation, and this is a way to generate trapped photons. If we stop midway, we go from E0 to G1, and we are sure that we have one photon in the cavity. We also know that if we wait as a function of time, the system evolves into a superposition of E0 and G1 with amplitude AT and BT, which are oscillating functions. And this is an illustration of the weirdness of quantum physics. We have a system which is neither in E0 nor in G1, but in a superposition of the two. And these superposition states are the states that quantum mechanics predicted, whose quantum mechanics predicted the existence, but they were very difficult to observe between atom and light because we had to be able to control the situation in this condition. And you see that if you have the atom leaving the cavity exactly at the time where A is equal to B, we get a situation which is shown here. We have at the same time an excited atom escaping from an empty cavity and a de-excited atom leaving behind a photon in the cavity. This state is called an entangled state. There is no way you can separate in this state the contribution of the atom, the state of the atom from the state of the field. It is called entanglement, and this entanglement has very profound consequences in a lot of quantum physics. So you see, it was well before people were talking about quantum information. It was back in the beginning of the 1980s, but we had the feeling that if we would be able to achieve this situation, a lot of things would become possible. Now, what about detecting this photon without absorbing it? So we had to start thinking about what happens when you detect a photon. And of course, we detect photons all the time. When you look at me, you are detecting all the photons which are scattered by my body. So this is something that we are used to do without thinking about it. But what happened in this case was described by Einstein in his famous 1905 paper. When a photon impinges on an atom, what it does is to expel an electron from the atom. And what we detect is this electron. It is called the photoelectric effect. And of course, this photoelectric effect destroys the photon. The photon is annihilated. And this is the fate of photons in general. They are destroyed. And this is also the case when you look at something. When you look at something, the photon comes into your eye, and it is absorbed in your retina and gives a signal to the brain, but the photon is dead. So the question we wanted to solve at that time was, is it possible to detect the photon in a gentler way? Not the brute force of just destroying it, but imprinting information on an atom without destroying the photon. And this is called quantum non-demolition in the jargon of quantum optics, to measure a quantum object without destroying it. And what we used to do that were the famous light shifts that I talked to you before. So I came back to this idea, which was developed by Claude Cohen-Tanuji. Is it possible to use the light shifts to detect photons without destroying them? And of course, when you use light shift, the atom and the field are non-resonant, so you cannot absorb the photons. You can just use the small energy shift produced by the photon on the atom. For that, we needed a very good cavity, and I will say a few words about the cavities that we developed back in 2006. This cavity is made of two copper mirrors facing each other. You see the scale here. The mirrors are very smooth. They are machined with a diamond machine which is able to prepare surfaces with a roughness of a few nanometers only. And on top of this very smooth surface, we sputter a thin layer of niobium, which is superconducting. And so we get highly, highly reflecting mirrors. In fact, these are the best mirrors in the world, and we obtained them in 2006. The light can bounce more than 1 billion times between these mirrors before being lost. And one way to give you an idea of how good they are, you know that light bouncing between mirrors is something that you can do in any elevator. When you are inside the elevator, you have two mirrors facing each other, and you can look at your reflection. And when the mirrors are not too bad, you see maybe 20, 30 reflections. With these mirrors, you would see 1 billion reflections, which means that you would see yourself reflected in something which is like the population of China. So it tells you how good the mirrors are. And the light is bouncing back and forth for about 1/10 of a second, or a little bit more. And so hundreds of atoms can cross the cavity during this time and extract information before the field decays. Of course, you have to do that with Rydberg atoms. And in fact, we use circular Rydberg atoms. So I remind you what these atoms are. You use laser excitation, and you promote the electron into this famous de Broglie circular wave around the nucleus. And the method to do that was again developed by Dan Kleppner in 1983. And so we use this method in our lab. But you see that if you prepare such a Rydberg state, there is no electric dipole. The electron is anywhere on the circle, and so the charge density for the electron has the same center of gravity as the nucleus, so you have no dipole. If you want to prepare a dipole, what we do is that we admix state E with the adjacent state G. So you see between E and G, you have only one node of the wave function which changes. And so if you prepare the superposition E plus G, which you perform by applying a microwave pulse, which mixes these two states, you have now a wave, you have now the interference between two waves. And of course, the waves will add at one end of the orbit and subtract at the other end. And now you have a kind of banana-shaped wave function with a large electric dipole. And this dipole is rotating at the frequency between these two states. And you see now that we really have the Bohr atom. We have a wave packet going around at 50 gigahertz, which is exactly what Bohr described in his 1913 paper. But you can also think of this rotating electron as a hand of a clock rotating on a dial. And in fact, this is a picture I want to use now, because what we will be doing to detect the photons without destroying them is to exploit the properties of an atomic clock made with Rydberg atoms. And for that, we use the light shift effect, which I described already. You see that what the light shift effect does is that when the atom enters in the cavity, state E will have its energy pulled in one direction, state G in the opposite direction, and these shifts are proportional to the photon number, that is, to the light intensity. This means that if you prepare a superposition of these two states, the frequency at which the superposition evolves will change by a quantity proportional to n, and it means that the phase of this superposition will acquire, this superposition will acquire a phase shift proportional to the photon number. I called phi naught here the phase shift per photon, and these Rydberg atoms are so big that the phase shift per photon can reach the value of pi, 180 degrees. This means that if you prepare a state superposition and let it cross the cavity, the state superposition will have one phase if you have 0 photon in the cavity, and the opposite phase if you have 1 photon in the cavity. And if you can measure this phase, that is, detect the orientation of this dipole, you will count the 0 or 1 photon without absorbing the photon. Now, to measure the phase requires an instrument in atomic physics called an interferometer. Interferometers are measuring phases. And we need an atomic interferometer. And this atomic interferometer is nothing but an atomic clock. And it was invented by Norman Ramsay back in the 1940s. And I give you here just the sketch of the setup. The cavity which contains the photons that we want to count is here. In this box, the circular Rydberg states are prepared. They drift one by one through the cavity, and here they are detected by field ionization. And as I said, we get one bit of information per detected atom. Now, there are two important ingredients here, which I show here. These two auxiliary cavities, R1 and R2. In R1, we apply a pulse of microwave, which prepares a state superposition, which admits E and G to prepare the dipole. Then we let the dipole drift across the cavity, and a second flash of microwave is applied here to find out what is the direction of the dipole after the atom has left the cavity. The succession of these two time-separated pulses applied to the atoms is called a Ramsay interferometer, and this is a setup that Ramsay had invented. What Ramsay had shown is that if you apply a sequence of two pulses and measure the probability for the atom to emerge in one state or the other, this probability exhibits fringes as you scan the frequency of the interferometer. And these fringes are the ones which are used in all modern atomic clocks to measure time. The experiment is not done with Rydberg atom, it's done with cesium ground state atoms, but you get narrow fringes, and if you lock your microwave to the central fringe, you get a microwave which gives you a tick which defines a second with a fantastic accuracy. So we are doing that here, but with Rydberg atoms. And you see, so what we have built is a clock which is delayed by the photons which are trapped inside, and the sensitivity is such that we get a change in the rate of the clock by 1 in 10 to the 7 per photon added. 1 in 10 to the 7 is about correspond to a shift of a clock of about 1 second per month. 1 second per month seems small for a registral clock that you are using in everyday life, but for an atomic clock, it's tremendous. Now, the clocks that Dave Wyland is developing at NIST have a precision of 10 minus 17 or 10 minus 18, which means 1 second per age of the universe, not 1 second per month. So you see, our clocks are very crude clocks for keeping time, but they are very good clocks for measuring light, as I will show you in the next slide. So you see here the fringes that we get from this clock if there is 0 photon. And if you have 1 photon in the cavity, the fringes are shifted by just half a fringe interval, which means that if you tune your interferometer at this point, you will have, with a high probability, the atom in one state if there is 1 photon, and in the other state if there is 0 photon. So by just looking at the state of the atom which leaves the cavity, you will know immediately whether you have 0 or 1 photon in the cavity. So we set up to do this experiment. And in fact, it's very simple. Where is this photon coming from? We don't have to do anything. We get this photon for free. Our setup is cooled down to 0.8 Kelvin. And in a cavity at 0.8 Kelvin, the Planck's radiation law, the Planck's black body radiation law, tells us that with a probability of 5%, you must have one photon in this cavity. This means that a photon pops in and out due to the interaction, to the thermal interaction with the cavity walls. So what you have is something like that. You get one photon in the cavity, then it disappears because it's absorbed, so you get a signal of a blinking photon in the cavity. 5% of the time you have one photon. How do you count this photon? You just keep sending atoms, excite them with the Rydberg, with the auxiliary cavities, and detect in the end whether the atom is in state E or in state G. And you see here a real trace. In real time, you see about 2 seconds time interval, and you see this kind of trace. You see that basically here the atom is in state G. You have no photon. There is some noise, of course. Sometimes the system is making a mistake, but clearly the photon appears and disappears, and you see here the period of time during which the photon stays inside the cavity. You can also find out with high precision the time at which the photon appears, which is called a quantum jump in the quantum theory. And you also see from this experiment that hundreds of atoms see the same photon. So it's really a quantum non-demolition way of detecting the photon. You also see that this photon has survived half a second in the cavity. And you might ask yourself, how is it possible that the photon has remained half a second while the cavity damping time is a tenth of a second? So you must, in fact, realize that the lifetime of a photon, or lifetime in general of a quantum particle, obeys to an exponential law. So, in fact, on average, the photon lives a tenth of a second, but a few photons corresponding to the tail of this exponential law can last much longer. And of course, here we have chosen voluntarily to show you the longest-lived photons we ever observed, which was half a second. So you see that to be a photon is a different fate than to be a human being. You can survive 5 times the life expectancy. Nobody would survive 5 times our life expectancy, so is it good or bad? I think it's bad to be a photon because due to the exponential law, the highest probability is to die immediately, just after birth. So I think I would trade off for life expectancy going like that rather than life expectancy going according to an exponential law. We can also measure larger photon numbers. So for that, we have to inject first a field in the cavity. And I just show you here how we do that. We have a horn, which is coupled to a microwave source, and we just send a burst of microwave in the setup, and some of the photons will be scattered on the edge of the mirrors and captured inside the cavity, which I have tried to show with this small movie. So you see, a field appears inside the cavity. This field does not have a well-defined photon number. It's a superposition of different photon numbers. According to this weird theory of quantum physics, the photon number is not well-defined because the phase of this field is well-defined, and you have an uncertainty between the phase and the photon number. So we prepare a superposition of photon number states in the cavity. Then we switch off the source, and you see that the field decays very slowly during 1/10 of a second. And during that time, you try to measure it. And to measure it, we send atoms one by one, and we measure the phase shift of each atom. And each atom provides some partial information. And after a few tens of atoms have crossed the cavity, we get enough information from the system to find out how many photons we have. But you see, it's an active process. It's not, at the beginning, the photon number is undefined, and the measurement itself forces the photon number to choose one given value. This is a measurement in quantum physics, and you will see it here how it happens. This is a real experiment. At the beginning of the experiment, we have a flat histogram because we don't know whether the photon number is 0, 1, 2, up to 7. So we assume complete lack of knowledge, and you will see what happens as atoms cross the cavity one by one. Each atom provides information, and using a classical argument due to Bayes law, we infer from the observation what is the most probable photon number distribution after the observation has been made. And you will see what happens. So it's a little bit like a horse race. You have 8 horses, and you will see which one wins the race. So you see at the beginning, it seems that these horses are winning. But then as you acquire more and more information, this is the green and the blue horse which are leading. And in the end, it is n equals 5, which wins this particular measurement. But if you do the experiment again, you will find another result. And this illustrates what Dr. Sorensen has said about a quantum measurement. God is playing dice with nature. The measurement is random. Einstein did not like that, but all the experiments performed in quantum physics, and in particular the experiments done with single particles or single photons, are vindicating this point of view. There is no way you can predict before the experiment which result you will find. Of course, if you do a large number of experiments, you reconstruct an histogram which gives you the average value, which should obey the laws of quantum physics. If you keep measuring, you see here it's the same measurement as before. You start from a flat distribution. The field collapses into a photon number state, here n equals 5. If you keep measuring, you keep finding the same result, up to the point where the fact that the cavity is not perfect will enter into play, and you will start losing photons due to imperfections. And when you start losing photons, you get quantum jumps, and it's a kind of staircase evolution. The system goes from 5 to 4 to 3 to 2 to 1 and to 0. And so we have observed thousands of such trajectories and verified all the concepts and principles of quantum physics with the system. This is a single field trajectory. So now I would like, during the remaining minutes, ask myself the question, is light an ensemble of photons, or is light a continuous wave? In fact, you see you have two aspects to light. The point I have emphasized up to now is that light is made of particles. Like I count them as I can count marbles in a box. I can find 1, 2, 3, 4 photons. So this is like particles. But at the same time, we know that light interferes with itself and that light has a phase, and this is a wave character. And the craziness of quantum physics is that these two concepts, particle and light, coexist together. And so which aspect occurs depends upon the kind of experiment that you are doing. Experiments in which we count photons emphasize the particle aspect of light. In other cavity QED experiments, which I will describe now, we can use atoms to measure not the intensity of the light, but the phase of the field. And in this experiment, we emphasize instead the wave aspect of light. And this dual aspect is something which has been expressed in a very deep way by Niels Bohr when he introduced his complementarity principle. In fact, Bohr said that which aspect you observe depends upon the experiment you are doing, and I will show you that by describing you now an experiment about the Schrödinger-Cat paradox. So let's come back to Bohr's complementarity and to the thought experiments that were alluded to in the introduction of this talk. You see here a picture of Bohr and Einstein discussing in a Solvay meeting, and as Dr. Sorensen has said, Bohr was the advocate of quantum physics, and Einstein was the devil's advocate. He always tried to find something amiss with quantum physics. And this is an illustration of complementarity. You see that depending upon your state of mind, you will read this light is a wave or light is a particle. And so the state of your mind is important. In Bohr's view, it's not the state of your mind, it's the status of your experimental apparatus. For some experimental systems, you will read light is a wave. For others, you will read light is a particle. And this is the essence of complementarity. I will just show you here a very simple experiment that Bohr and Einstein discussed in 1927. All physicists know about the Young double-slit experiment. You have here a source of particles which cross a screen with two slits, and then they recombine and they form fringes on the last screen. This experiment exhibits the wave nature of particles. If you have fringes on the last screen, it means that the particle behaves as two waves which have crossed each of the slits and which interfere with a phase difference depending upon the difference of path between the two slits and the screen. Now, Einstein tried to find out a way to find at the same time the trajectory of the particle and observe the fringes. He said, let's assume that the upper slit is on a movable device with springs here. What will happen if the particle hits the upper slit? It will kick it by being scattered off the edge of the slit, and the slit will start moving, bouncing up and down. And so if you see the slit moving, it means that the particle went through this slit. So you will have the trajectory, And since the particle has been able to go through, why not see at the same time the fringes and the trajectory, which would be in contradiction with complementarity? So Einstein's idea was very simple: to find the path, detect the momentum transfer to the movable upper slit. Bohr, of course, did not have too much to reflect to answer. He said, if you want to do that, you have to define the slit initial momentum with a very small error, delta p, because the momentum change will be small. So if you have an uncertainty in the initial momentum, you will not see the difference. But then, according to Heisenberg uncertainty relation, if delta p is small, delta x has to be large. In other words, what we call the zero-point fluctuation of this slit will be large enough to blur the path difference and to make the fringe disappear. So what Bohr was able to show to Einstein is that within the framework of quantum physics, in which Heisenberg uncertainty relation play an important role, there was something which was preventing the simultaneous observation of the fringes and the trajectory. So inside quantum physics, you have something which enforces complementarity. What I also want to stress is that this experiment is an experiment about entanglement. You see that when you do such an experiment, it means that the particle is crossing the two slits at the same time. So the particle is in a superposition state of the state in which it crosses the upper slit and the state in which it crosses the lower slit. But if you have the moving slit in the setup, it means that the particle is not alone in this game. The particle is correlated to the slit, and you see that if the particle crosses the upper slit moves, whereas if the particle crosses the lower slit, of course, the upper slit does not move. And now the state of the particle plus the slit is an entangled state. And in the modern language of quantum physics, what kills the coherence is the slit-particle entanglement. It's because you entangle the particle to a large system, which can be an environment here, another part of the setup, that you lose the ability of seeing interferences. I also want to stress that we have here a Schrödinger cat. The slit is a big object, which, due to the interaction with a single particle, is transformed into a superposition of being moving and not moving at the same time. And this is exactly the idea that Schrödinger developed in his tale of the Schrödinger cat. Of course, Schrödinger was more clever, so to speak, because instead of talking about an inanimate slit whose fate does not interest anyone, he spoke about the life or death of a cat, which is much more striking, but it's the same story. Schrödinger cat story is the same. You have a single atom. If the atom is excited, nothing happens to the cat. If the atom is de-excited, it triggers a setup which kills the cat. And if the atom is in a superposition of being excited and de-excited, the cat must be in a superposition of being dead and alive. And you have exactly the same entanglement as before. And this story, which tells you about superposition and entanglement, raises also the issue of the boundary between the quantum and the classical world. Nobody has ever seen a cat being suspended between life and death, so it means that when the system is large enough, this kind of superposition do not appear, and this is due to decoherence. The coupling to the environment destroys the quantum coherence very fast. So how can we do that with our cavity QED setup? Let's suppose that we have a non-resonant atom a single atom crossing a cavity which contains a field. So I've shown you here the standing wave of the field. The atom is going across the field, and when it gets into the cavity, the energy of the atom is slightly changed. This is a light shift effect again, which means that the atom is flying above a kind of potential well, which means that when the atom enters into the cavity, its kinetic energy is increased because of conservation of energy. And this kinetic energy increase is proportional to the photon number, of course. So where is this energy coming from? You must have energy conservation. This energy can come only from the field. It cannot come from a change in the photon number because the system is not resonant. So it can only come from the fact that each photon sees its frequency changed. It becomes omega minus delta instead of omega, and if you have n photons, the loss of energy of the field is nh bar delta. Then you have to equate these two quantities for energy conservation, and what you find is that the change of frequency of the field is the same as the change of frequency of the atom due to the non-resonant interaction. So the two systems interact with each other and change each other's frequency, which is a very simple effect. And it means that when the atom crosses the cavity, the field acquires a phase proportional, a phase shift, which is proportional to the time it takes for the atom to go across. And this phase shift can be as large as pi or pi over 2. And moreover, this phase shift depends upon the state of the atom. It takes opposite signs depending upon whether the atom is in one state or the other. And now you see how Schrödinger cat comes into play. If you send an atom in a superposition of two states, the field will acquire two phases at once. To describe the phase of a field, I need a last mathematical ingredient, which is the Fresnel plane and the Fresnel vectors. You see here three classical fields which have the same amplitude and which differ by their phases. And all electrical engineers know that in the complex plane, you can represent these fields by arrows whose lengths are proportional to the field amplitude, and direction gives the field phase. So you see these three fields, which are 120 degrees out of phase, are represented by three vectors like that. In quantum physics, this picture is slightly modified. You still have a vector, but the tip of the vector is fuzzy because the amplitude of the field cannot be well defined at the same time as a phase. And so the tip of this vector belongs to a Gaussian distribution, which is the best approximation you can have of a classical state. And this distribution is called the Wigner function of the field. So classical fields, which are well-defined phase, are represented by Gaussian distribution in phase space. So what happens now when we send a single atom across our cavity? We first prepare this small coherent field, a small arrow with a fuzzy tip, and we send one atom. And we prepare this atom in a state superposition in the first Ramsey zone. Then we cross the cavity in state superposition. And you see now that when we get out, we have an entangled state. Either the atom is excited with the phase pointing in one direction, superposed to the atom in the other state, and the phase pointing in the opposite direction. And you see now that you can consider that the state of the atom gives you an information about the phase of the field. And if you detect the state of the atom here, you will find either this phase or that phase. This would be the classical result. If you want to be more clever, you don't detect at this point. You let the atom cross the second Ramsey zone, which admits the two states again, and you detect the atom afterwards. So you use a Ramsey interferometer in another way, and then you detect. And you see now that when you detect at this point, you are not able anymore to know in which state was the atom when it crossed the cavity. So you stay in a superposition of two possible phases for the field. And so you see again, this is again a play with complementarity. Either you measure here and you display the particle nature of the atomic trajectory, either this state or that state, or you admix the two states in the second Ramsey zone and you keep the quantum coherence. And we did that experiment, and just since time is passing fast, we were able to reconstruct the Wigner function of this cat by making many, many measurements and using a modified version of our QND measurement I don't have time to discuss. And we get this kind of Wigner function for the state of the field after the atom leaves the cavity. You recognize the live cat and the dead cat. And these are the cat's classical components, so to speak. In between, you have a large quantum interference, which shows that it's a coherent system. And this is done with a distance between the two classical components going up to 10 or 12 photons. So it's not a large system, but it's what we call a mesoscopic system. And moreover, we're able to study the decoherence of this cat by taking snapshots at increasing time after the state preparation. And you will see here the time scale, 1 millisecond. You will see that the fringes between the dead and the live cat are disappearing rather quickly. And after about 20 milliseconds, we have just a statistical superposition of the two states, and we have lost the coherence. And this obeys the theory which was developed by Wojciech about decoherence of harmonic oscillators. So I would like to conclude now by making some connection with thought experiment. Dr. Sorensen alluded to what Schrödinger thought about thought experiments, and I'm quoting him here. We never experiment with single electrons, atoms, or small molecules. In thought experiments, we assume that we do, and it always results in ridiculous consequences. So I must say that for Dave Wineland and for myself, the consequences were not that ridiculous, but Schrödinger, I was surprised to see that Schrödinger wrote that in 1952, because at that time, single particles were detected routinely in accelerators, in cloud chambers, and so on. But Schrödinger knew that, but he said it's completely different there. In this experiment, it's a kind of post-mortem experiment. We see the traces left behind by particles which have decayed, and these observations are a little bit like what a paleontologist is doing when it takes the bone of a dinosaur and it tries to reconstruct the living dinosaur from the bones. And in fact, Schrödinger wrote it. It said, "It is fair to state that we are not experimenting with single particles any more than we can raise each other in the zoo. We are scrutinizing records of events long after they have happened." So the kind of experiment I described you today and the kind of experiment that Dave Wineland is doing is, in fact, controlling a zoo of particles in vivo and not post-mortem. And this has become possible, of course, because of technology. Tunable lasers, fast computers, in the case of our experiment, superconducting materials. And I think I want just to stress the fact that these technologies come from quantum, the knowledge of the quantum world. So we have here a kind of virtuous circle. The knowledge of the quantum world has developed quantum technologies which allow us now to come back to the fundamental effects and to study now what happens at the microscopic level in real experiments. And so I just want to make a kind of connection between the experiments that Dave Wineland and that is doing in Boulder and that we are doing in Paris. In fact, these experiments are two sides of the same coin. In Paris, we are manipulating non-destructively single atom, in Boulder, Dave Wineland is manipulating single atom with photons. He's trapping single ions and use laser beam to manipulate them. And in Paris, we do the opposite. We manipulate single photon with atoms. So you see here a sketch of Dave's experiment. You have a set of electrodes which keep ions trapped at well-defined location, and lasers are used to cool these atoms and to trap them and to detect their change of state by the large scatter. And in Paris, we do the opposite. We trap the photons, and we use a beam of atoms to extract information from the field. And in both cases, we are performing in vivo physics. We don't kill the atoms. We don't kill the photons. And in both cases, we use light-matter interaction at the most fundamental level. But I also want to stress that we are not alone, and many groups in the world are controlling single particles for quantum information with ions, photons in cavity, and so on, but I don't have time to discuss that. And I just want to say also that we are not only physicists. You see here, we are here with Dave Wineland and his wife, Sedna, and we went to visit a painting exhibition. So you see, we have other interests than pure physics. Art is also very important. The question that I want to finish with is that, is this the beginning of a quantum computer? Can we think of a computer which would be in a kind of Schrödinger cat state, computing on several channels at the same time and having an interference of the outputs to give you the result? This is, of course, a dream of theorists, but it remains a dream due to decoherence. So there is a lot of studies being carried on, but nobody knows what will happen. And I think this is a very important statement about basic research. What I can say is that the ideas of cavity QED are now being extended to what is known as circuit QED, where Rydberg atoms are replaced by artificial atoms, which are made of superconducting circuits. And you see here just a picture of such an experimental scheme. These small black areas here are the superconducting qubit circuits, which behave as our Rydberg atoms. And these strip lines are resonators, which behave as cavities. And in fact, the physics of this system is quite similar to the one I've described to you today. But it's, of course, more scalable and more practical. And if there is an application, it will more likely come from this kind of setup than from the one I have been discussing. In fact, by shuffling photons between real or artificial atoms, it may lead to application in quantum information. And people in the field of circuit QED have been able to factor 15 with this kind of system. And they have found, not surprisingly, that 15 is 5 times 3, with a large rate of error. But it's not a problem because, you know, it's difficult to factor, but it's easy to check. So even if you are able to compute with a 1% probability of getting the right result, it means that you have to do the experiment 100 times to find the factors, which will be already very nice. But of course, this is just a toy experiment. So I would conclude by stating that blue sky research is unpredictable. I will give you another example. I told you nobody knew what to do with the laser in the 1960s. About 10 years later, highly transparent optical fibers were developed. Then computers became more and more powerful. And when you integrate these three factors, you get, of course, the global communication networks. But if you had told to my man who developed the first laser, I want to develop the internet, of course, it was not the right way to go. He did not know what you would be talking about. He would not have known what you would be talking about. So research is, by definition, serendipitous. The world needs new technologies. There is no doubt about that, to solve the big challenges. But these new technologies can emerge only from blue sky research, which is not directed. And this blue sky research needs two priceless ingredients, which is time and trust. You need to give time for this experiment to develop. I gave you here an example of experiments which took 30 years to be developed. And you need to be in a place where people give you the time, that people trust you. And research thrives in such places like our lab or like the lab of Dave Rhinon, the NIST lab, where these ingredients, time and trust, are present. And I must say that these ingredients are not really favored by the global market, which emphasizes speed and fast results, which is completely contradictory with the spirit of research I am trying to illustrate here. There are some exceptions, and I think the European ERC grants, which provide grants on curiosity-driven research projects, is very helpful, and our experiment would have been impossible during the last 10 or 15 years without the help of European money. And in particular, I want to acknowledge the DECLIC project, Decoherence of Light in Cavities, which has helped us do the last stages of these experiments. When I say us, I want also to acknowledge my co-workers, Jean-Michel Raymond and Michel Brune, who have been with me for many, many years, and all the team of fantastic students and postdocs, which I've been working with during all this time. Of course, the postdocs are renewed, and here I'm very proud to show you the complete list of people who have been postdoc and student in my group for the last 40 years or so. And I'm especially proud of the fact that about half are foreign, and they represent 20 countries in the world. So really the big reward in the career of a researcher is to have this opportunity to connect to all kinds of people working everywhere in the world and sharing the same passion for curiosity-driven research. And I want to acknowledge that at the end. Thank you very much.
Thank you very much for a very nice talk. Unfortunately, we're running a little bit short on time, so I will skip my questions and instead ask the audience for questions. So I think we have one here.
Thank you very much. Please, Professor, be so kind to tell us, would it be possible to open one more question regarding these liaisons? You said it's a question, is the light wave or particle? And now my question is, would it be possible some of these experiences to connect somehow quantum and solid mechanics? Because, for example, cavities are very useful for examination of the failure. And in solid mechanics, failure avoidance is the key question, almost for materials or structures or whatever. So what is your prediction in, let's say, that way? Thank you.
I'm not sure I understand really the question, but I think at the level of light, the answer is light is, as I said, has at the same time a particle and a wave character, and the two are mixed in a way which cannot be described in classical terms. The problem we have in our everyday language that we are trying to use words which are coined by our classical intuition, and to use this word to describe a microscopic word to which this intuition does not apply. So that's, I don't think the system cavity plus atom inside behave in a quantum way is in state superposition. And it's not easy to do because you have to avoid all the perturbation which make nature try to become more and more classical, decoherent and so on. But in fact, this is the way nature behaves.
Thank you.
So, one last question, perhaps. There's a burning one.
Or maybe you can ask yours.
So, I would like to ask you, so you've been doing this for 30 years, so what do you feel is the most important thing you have learned?
I don't know what is the most important, but I have been amazed to learn that these people, Einstein and Bohr, were able 80 years ago to get the right theory, in spite of the fact that they did not like it. Or at least some of them, like Schrödinger, Einstein, did not like it. So I think this is a triumph of human mind. The fact that by using pure rational logic, you are forced to accept ideas that you don't like. And I think this is very deep. And it's also very important to realize that classical logic led them to that. They did not need a quantum computer to understand quantum physics. So that's what I can say in a nutshell.
All right, unfortunately, we are out of time, so let's thank Professor Haroche once again.
Thank you.